Any news or
Right, ladies and gentlemen, welcome to another edition of the CLSP seminar. Today I have the pleasure of introducing Dr. Partha Niyogi. He's from Bell Lab Lucent Technologies. He started his research career working on learning theory and language acquisition, and he did his PhD from MIT with Tommy Poggio, although he did a lot of work with Bob Berwick as well. Since then, or rather more recently, I got to know him for his work in speech recognition, and in particular, sort of looking at the recognition of phonetic segments and looking at how one can build perhaps articulating modules, if that's a good way to describe it. And today he's going to talk to us about a computational model of human speech recognition.
So part of my goal today is really to also promote discussion on how we might do speech recognition differently. And in particular, if there are ways of doing speech recognition that might allow us to bring together progress on the scientific question of understanding how human speech and language works, and progress on the technological question of building a machine that has those capabilities. Now, part of the reason one is looking for alternative approaches is not just a whimsical desire to be different. It's really based in the belief that current approaches to recognition are unlikely to yield a general solution to the problem. So I'm going to try and give you over the next hour or so a sense of why I feel that way, and tell you a little bit about an approach to speech recognition that some of us are pursuing. It's based on the notion of distinctive features. I'll tell you what I mean by that, and give you an idea of the motivation behind the approach, some of the technical sub-problems that need to be solved in order to make such an approach viable. And hopefully at the end of the day, you'll also get a sense of how such an approach will engage the traditions of research in psychology and linguistics in a way that current approaches really don't. So given all of that, let me begin with a thought experiment. So imagine a child who grows up on a desert island with no access to any modern amenities, who learns language in the natural way, in its natural environment from his or her parents. And imagine that such a child now comes to town for the first time and uses a telephone and decides to speak to his parents on the telephone. Will such a child completely stop understanding his parents, and will it take him days of retraining before he can start understanding his parents again? Now, the question is clearly rhetorical. You all know what the answer is. Humans have an amazing ability to generalize to novel acoustic environments that they have not encountered before. Okay? The key word here is generalization. And in contrast, modern speech recognition, which has made a lot of progress so that you can buy for $100 speech recognition systems that seem to reasonably work, they have some very disturbing aspects. So for example, if you change the microphone, the recognition rate drops dramatically. And people who work in the field have their own stories to tell. I have these two numbers that I got from a master's thesis that was done at MIT some years ago. Apparently the SRI system on this ATIS domain, the word error rate dropped from 23% to 91%. I find this hard to believe, but that's what was reported. On the Wall Street Journal Sphinx, the word error rate dropped from 8% to 39%. Now these sorts of things people can sometimes deal with using techniques like textual mean subtraction and so on. When you go from regular channel speech to telephone speech, the recognition is quite dramatic, and basically we don't know what's going on, and we don't know how to handle it. Another fact about speech recognition, which is often swept under the rug, is that raw acoustic phonetic error rates are really quite low. So if you take away the top-end language model that constrains sequences, and you just measure acoustic phonetic accuracy of a standard off-the-shelf speech recognizer, recognition rates drop a lot. So for example, a alphabet recognition problem I worked on, the error rates drop from 86% to 68% when you change the back-end language model. And of course, again, there are many, many examples of what how much this error rate could drop in different domains as the language model is removed. So basically, the acoustic phonetic error rates are really very low. The problem is far from being solved. Now, humans, on the other hand, can decode nonsense words. They learn new words. Okay? We would never learn words correctly if we didn't have pretty high acoustic phonetic decoding abilities. The other thing, which is also very disturbing, especially from a statistical point of view, given that most techniques in speech recognition are statistical, is that a typical modern speech recognition system has 2 to 4 million parameters. Now, that's a hell of a lot of parameters. And there isn't enough data to estimate those parameters correctly. And as far as I can tell, every statistical law is violated in estimating those parameters. Now, you can smooth, you can regularize, but essentially we are grossly undertraining our systems, and little wonder that they don't generalize. So, most of you, of course, this should really not come as a surprise, but most of you know that the current approach is based on hidden Markov models. And roughly speaking, what this reduces to is that you take the speech signal and get a vector time series representation for it. Now, the vector could be Kepstrel front end, it could be Kepstra, Delta Kepstra, and Delta Kepstra, as is currently fashionable. It could be any other thing, really. But it's a vector time series. And this is supposed to be the output of a hidden Markov model, which is the generative process. And basically, you estimate the parameters of the hidden Markov model, and recognition is inverting this generative process. Now, if you think about it for a moment, this basic model of speech recognition, okay, 3-state left-to-right HMMs with output mixture of Gaussians, with a Kepstrel front end and a n-gram back end, hasn't changed in maybe 15 years. Okay? So what's been going on for the last 15 years? In 1985, this model, with all its details from an algorithmic point of view, were exactly the same as they are today. So I don't know what the answer to that question is. A lot has changed in terms of adapting these models perhaps to different circumstances. The computers have gotten faster, so there are data caching issues that come up. We've tried out a variety of problems, different tasks, large vocabulary, small vocabulary, and so on. But in some sense, the core technology has not changed. And it hasn't really solved the problem. And so maybe it's time to try and think of how we might do speech recognition differently. So what we want is a machine that takes as its input speech and produces as its output. It's not clear what it should produce as its output, actually. But let's say, for the sake of argument, it should produce the words. Now, that's what we desire of such a machine. And speech is easy enough. It exists all around us in the physical world. We measure it in a microphone, and we stare at it in MATLAB or Entropics or your favorite software. But what is considerably less clear is what are words. Now, you might be tempted to say words, why don't we just look them up in a dictionary, and those things in bold black print on the left-hand margin, those are the words. But imagine now that you go to a community which has no writing system at all, and you go to this community and you try to figure, and they have been communicating and have had an oral tradition for years. You go to this community and you try to figure out what are the words. So words don't really exist in the physical world at all. They exist only in the minds and heads of speakers and listeners. And so we really have to get into our heads and ask, what are words, where do they live, and how are they represented? And this is exactly the question that linguistics and psychology asks. And so a rough answer that they provide is that there is a linguistic hierarchy, and there are words, and words are made up of syllables, and syllables are made up of phonemes, and ultimately the fundamental atomic units out of which all of language is composed are these so-called distinctive features. Okay? So one way to view such distinctive features are as natural phonological classes. Okay, and I'll sort of give you some examples of such natural phonological classes. So for example, in phonology, here's the classical English plural rule. You have words and you have their plurals, and you make lip into a plural by adding an S, lips, lists, maniacs, telegraphs. So these take on an S, and club and herd and colleague and love takes on a Z. And now when you try it on a new word which you've not heard before, like wug, all native speakers of English tend to add a Z. And if bark were a word of English, all native speakers would tend to add an S. And so clearly we are using a rule of some sort as we are generalizing to new words which we've never encountered before to make their plural form. And one can ask, what might the nature of such a rule be? And here are two candidate rules. You look up the last segment of the word, and if it is P or T or K or F, you add an S, and if it is B or D or G or V, you add a Z. But here's another candidate rule. You look at the last segment of the word, and if it is unvoiced, you add an S. If it's voiced, you add a Z. It turns out that this is a rule which has reasonably good generalizing power, but the point to note really is that phonemes of a language group into natural phonological classes as they participate in this phonological process of pluralization. So you get natural phonological classes from the point of view of phonology, and all of phonology really is in some sense developing this theory of natural phonological classes as they participate in phonological processes. Now, switching from phonology, so that's one sort of whole area of research that we will ultimately make contact with. But here's an argument from psychology. So this is a classical experiment by Miller and Nicely years and years ago in '55. And here are different sounds, different phonemes of American English produced, and this is how they were judged by speakers under a variety of acoustic conditions with noise and different signal-to-noise ratios. So this was a P, T, K, and so on. I don't know if you can read it, but you might not be able to read the details, but you will notice that the confusion matrix has a block diagonal structure. So phonemes are grouping into natural classes from a perceptual point of view. Okay? So the argument from phonology has a completely different basis. This is an argument from perception. Okay? And again, phonemes are grouping into natural classes. And of course, people have for a long time grouped phonemes into natural classes from an articulatory point of view, depending upon how they have been produced. And so labial sounds like p and b and m and so on group into one class and so on. And so phonemes can be grouped into these natural classes, and the names for these equivalence classes are essentially distinctive features. Okay? The interesting thing is that they group into the same classes phonologically and perceptually and from an articulatory point of view. So, you know, walks like a... So here's the point of view. So you have the broad classes, for example. These are the distinctive features. Stops, affricates, fricatives, nasal, so on. For broad classes, the classes are associated with natural articulatory gesture. So all stops are produced by having a complete closure of the oral cavity at some point in the oral cavity. All nasals are produced by coupling of the nasal cavity. So because they have some natural articulatory gesture, they have associated an acoustic correlate. And that acoustic correlate is what we are after. Okay? And we are going to construct detectors for these particular acoustic attributes for these natural classes, and then we are going to use them as hooks to access the lexicon. So that's one part of the story. Let me point out some basic principles that we believe to be true of human speech perception. Okay? So one thing, I've tried to argue that it's reasonable to represent the lexicon in terms of distinctive features. Okay? I've also argued that features have an articulatory status which might be insightful in understanding the acoustics. 3, 4, 5, and 6 are other properties of the speech signal that come out of readings in acoustic phonetics and perception. Acoustic cues are local in the time frequency plane. What do I mean by that? The cues that tell you how to discriminate between an ah and an oo reside in a certain local part of the time frequency plane so that you can perturb irrelevant portions of the time frequency plane and not affect the percept or the difference between ah and oo. So you could actually take the speech signal and entirely filter out all the high frequency sounds, and ah and oo perception would remain intact. So making global distance measures across frequency is a bad idea. Okay, and that's exactly what modern speech recognition does. It constructs cepstral measures and takes Euclidean distance or a Mahalanobis distance between cepstral measures as they construct this. So you want local, it's obviously local in time. Phonemes are local in time anyway, but it's also local in frequency. Acoustic correlates of the features are at different time scales. So stop consonants, the burst of stop consonants could be as short as 5 milliseconds. When you're dragging along a 30 millisecond window moving every 10 milliseconds, there's no burst that you're picking up, okay? I don't know what you pick up, but you don't pick up a burst. So in contrast, vowels might have resonant sounds, they are periodic, they have a completely different time scale. So we need to have multiple time scales as we represent the speech signal. Regions of change or transition in the signal are perceptually salient. And so they should be given some kind of a special status beyond, status that's beyond a mere sort of nod in that direction by taking derivatives of cepstra. Cues for the different features are heterogeneous and class specific. So these are all principles that we believe to be true of human speech and language. And the challenge is to give computational expression to these principles. So what we would like to do, how do we know that how do we actually measure progress? Okay, so I'm telling you that there are all these principles and we would like to give computational expression to this. How do we actually determine, as we go down this path, that we are making progress? What are the criteria? So at least I will have to convince you that we get higher recognition rates. So that means by actually measuring these alternative acoustic properties, we are able to better separate sounds that were not very well separated in the cepstral domain. Or that we are able to get robust recognition rates. They are invariant to microphones or telephones or so on. Or that we will get simpler, drastically simpler models so that there are much fewer parameters to estimate, and we're not going around estimating 2 million parameters. And ultimately, actually, in some sense, insight. Now, insight is this, mystical thing that's hard to define, but we all know what it is when we get it. So at the end of the day, hopefully you will have some insight into what works for some of the problems that I'll talk about. So the first thing that Vishnu Atal told me when I sort of was talking about these things is that if you can prove for even one feature that you get better separation, that it actually does something for you from a purely acoustic phonetic point of view, is able to better separate classes of sounds that are confusable using cepstra, then you would have made progress. So that's the first thing I worked on. Okay, we need to ask the following 3 questions. What are the acoustic correlates of a particular distinctive feature? Do such correlates provide better separability than traditional spectral features like cepstra or spectra or any other natural transformation of them? And can such correlates be reliably extracted in an automatic way in a speech recognition system? So the particular feature I'm going to look at is actually deliberately made simple. It's the voicing feature for stop consonants in an alphabet task, which means that there is always an E after these sounds. So it's P versus B, T versus D, and K versus, there's no G actually, but K versus G. And this, of course, is one of the old results in acoustic phonetics, but I'll just give you some feel for it. If you look at the waveforms for T and D, there's a closure, and then there's a burst as the stop is released, and then you go into the vowel, the E portion. Okay? The voice onset time is the distance between the onset of the burst and the onset of voicing. Now, there is some disagreement about precisely whether it's the onset of the voicing or the beginning of the first formant, but that's sort of irrelevant for our purposes. Roughly speaking, we can take it to be the onset of voicing. And so it's a temporal measure. It's a distance between 2 points in time, the onset of the burst and the onset of voicing. And that, in the acoustic phonetics literature, a phonetician would tell you what separates a P from a B is the voice onset time in syllable initial position. Okay, and all these stop consonants are in syllable initial position. Of course, in speech recognition, we've stopped listening to phoneticians for a long time. So what do? We actually measure cepstra, or spectra, it doesn't matter. So I've taken the same spectrum the same burst and actually measure the spectrum of the burst centered at the burst. So these are the burst spectra of a P and a B. Now, you can see that the peaks all roughly lie in the same region. They're actually very similar to each other in overall shape. And it's not surprising because the overall spectral shape is a function of your vocal tract shape. And for a P and a B, you have exactly the same vocal tract shape, so you will get the same global spectral shape. And if you're further smoothing this out by actually taking Kepstar, you will get very, very confusable things. So if you actually, so there's a database at Bell Labs called the KBB database, which is one news reader, I believe, who speaks very clearly. And so on this particular single speaker database, we computed the voice onset time. It's a segmented database, so you can actually get lots of P's and lots of B's. These are actually T's and D's, but it doesn't matter, it's the same point, for that speaker. And this is how the, or maybe this is P's and B's actually, it's around 20. So these are the B's and these are the P's distributed. And you get almost perfect separation for this one very clear speaker on clean speech. Now this sort of perfect separation in the acoustic space is very rare in speech. Okay? Usually you just see a mess. This is a single clean speaker. You can of course now do the usual thing, go to, this is actually Timmit, so there are 600 speakers in Timmit. And you can actually take spectra of P's and B's and compute voice onset time for P's and B's on the Timmit database, construct probability models in the spectral space, construct probability models in the voice onset time space, plot likelihood ratios, and these are the distributions of likelihood ratios. Okay, the reason we need to construct probability models in space is that these two spaces, one is in a 39-dimensional Kepstar space, and one is a one-dimensional voice onset time. So we need to reduce the dimensions to the same thing so that we can compare them on a common denominator. So these are actually the likelihood scores. This is the separation between D and T in the Kepstar space, and this is the separation between D and T in the voice onset time space, the dotted lines, okay? So this is the separation in voice onset time, and this is the separation in Kepstar space. Okay? Now, as a practicing hard-nosed speech recognizer, which feature would you like to use? So, I think we've not been listening to phoneticians enough.
Actually, we listened to phoneticians, tried to do it their way, were disappointed, and then we started listening.
Right. So it's time perhaps to start doing it our way, but listen to them at the same time.
Well, I mean, after all, you are making very simplified assumptions here, that you know how to put this separation into the whole system. I mean, after all, we're using HMMs for certain reasons. Because things fit in and we can build the whole system and everything. Well, so.
Okay, so here's a two-pass speech recognition system. One pass is a standard HMM, okay, with the standard way. You use it to actually segment your sound, and then you reclassify, and then you have a second pass which does separate feature extraction on it, and computes the voice onset time and reclassifies stops as voiced or unvoiced using this different classifier. And this actually reduces error rates along this dimension by 50%, along the voice onset time dimension by 50%. Now, this is just one feature, okay? I'll be very humble. This is one feature in a very particular acoustic-phonetic context. It's the voicing feature for stop consonants where they're all followed by E and they're all in syllable initial position. But for that one particular feature, there is a dramatically different acoustic correlate that works much better for you than anything you would do if you used a one-size-fits-all representation that modern speech recognition forces you to. Okay? So, we need to discover what the acoustic phonetic correlates for the other features are in other contexts. We need to understand the sources of variability in each of those features, because even voice onset time does have variability. And we need to discover principles for organizing such features and we need to be able to extract them automatically. So now I'm going to describe to you, I didn't tell you many details. The voice onset time was defined as the distance between 2 points in time, the onset of the burst and the onset of voicing. Now I didn't tell you how you would actually get the onset of the burst automatically from continuously spoken speech. So this is actually the problem of stop detection. And I'll spend some portion of time on this. So the problem is very simply stated. This is joint work with Mohan Sondhi and Chris Burgess. And the problem is, given continuous speech, you want to pull out all the stops. So you want to actually, given continuous speech, mark out all the points in time when there is a closure burst transition. Okay? Now, because we know how stop consonants are produced, we know that there is a closure and there is a burst. There's a point where you close your vocal cavity, a sharp drop in energy, and then a sharp rise because you have the explosion associated with the burst. So if you do the first obvious thing of actually taking energy profiles, and then basically taking derivatives in time of energy profiles, you will get a reasonably good stop detector. And then what you would get is something like what is called the burst landmark in the approach taken by Ken Stevens. Okay? And it works reasonably well. Now, the point we sort of noted was that a derivative of the energy profile is only one kind of a linear operator. So maybe there is an optimal linear operator, or maybe there is an optimal nonlinear operator that you might want to use in the speech signal to actually extract this. So here's the speech signal. You want to come up with a representation in which the particular acoustic attributes of stop consonants best express themselves. And such a representation, we decided, and we can argue about this, what representations are good, has three components. This is total energy, this is high frequency energy, and this is something called the Wiener entropy. Now the total energy and the high frequency energy basically would capture the profile of closure and burst. The Wiener entropy actually is a measure of spectral flatness, and it separates periodic sounds from aperiodic sounds. So these three measurements together would tell you essentially that you're now going to look for a changing energy profile associated with a noisy burst. These are all computed with 5 millisecond windows moved every 1 millisecond, because remember, these bursts can be actually very, very sharp. So the input is this sort of a time series, and you want to hit this with an operator which produces a one-dimensional output, which will be 0 all the time, and it will be 1 whenever a closure burst transition occurs. Okay, so that's the problem. So this is speech. This is a representation that you built based on your intuitive understanding of what the phonetic acoustic correlates are that you're looking for, and then you want to hit this with an operator so that it produces something like this. So we're going to define a class of H operators, which are basically going to look like this. It's going to operate on a 2T stretch of the signal. Okay, so S is the input time series, and you have Sn minus T to n plus T, and the output will be D subscript H of n for the operator H. Okay, so the operator H is actually a function from R to the 3 2T plus 1 to R. Now this 3 is because there are 3 dimensions, this 2T plus 1 is because you're basically looking at a 2T plus 1 length window. Okay, so this is a function D, and this is the output DHN when this operator H is applied to the signal. And what you want is this DHN should be as close to the desired output YN, which is that 0, 1 value spike, okay, as you want. So you want to choose the optimal operator by minimizing over a class of possible operators script H. Something like this, the distance between DH and Y, and you will get the optimal operator. And because this is actually an L2 norm, and because the conditional density minimizes the L2 norm, DH op will actually be an approximation to this quantity. It's the expected value of Yn given the speech signal. But because Yn is 0, 1 valued, it's actually just simply the probability Yn is equal to 1 given Sn. Okay? So it's the probability at every point in time that this is a closure burst transition. So if you set things up this way, you're basically searching for an optimal operator, and once you're done, that optimal operator will be the output when that optimal operator is applied to the speech signal will be an approximation to the conditional density, conditional probability of a stop given the speech signal at every point in time. Then you can do with it what you want to. Okay? Now, some things still remain. There are two questions that I still have to resolve. One is that I haven't told you what this class script H is. Okay? The other is we actually don't have the underlying probability distribution, so we actually can't compute the expected value of d minus y squared. So we have to approximate this expected value in some way by an empirical risk, and I'll also have to define this class script H for you. So let's first start with, so if we had the expected risk, and if we were able to minimize it over class, we were done. We don't have the expected risk, so we have the empirical risk. So we'll construct an empirical risk, and we could actually minimize the empirical risk over the class script H. But actually, as it turns out, due to the work largely of Vapnik and Chervonenkis, but several others working in empirical processes, this is not as good an approximation as this is. So rather than, when you want to actually minimize E true, which is the true expected value, you make use of this large deviations inequality, which relates the empirical risk to the true risk by a quantity which relates to the VC dimension of the class of script H. So the VC dimension of the class script H is a measure of the complexity of the class script H. So essentially, rather than minimizing the empirical risk alone, which is what you would do in standard minimum error training, you actually minimize it with the empirical risk and an additional term which depends upon the VC dimension. And this inequality comes out of the work of Vapnik and Chervonenkis. Okay? So you penalize complicated families of function script H. Okay? The second thing you do actually is that you build a hierarchy in your class script H of more and more sophisticated functions. H1 is the simplest in your hierarchy, H2 is more complex, H3 is more complex. And you have this nested hierarchy, H1 in H2 and H3. And script H is, of course, the union of all of this. It contains all of this. And so you're basically searching through this hierarchy to find the least complex class which both fits your data and satisfies this complexity bound. So you're basically doing model selection, and you're doing model selection to actually control the overfitting problem. Because you can get anything to fit your training data, okay? So how do you actually get something that fits your training data and yet generalizes to novel examples? So that's what we do about the fact that we don't have the expected risk. We have a controlled estimate of the expected risk using the empirical risk. Now I have to tell you what the class script H is, which has been mysterious all along. So let's consider a very simple family of functions script H, which are just a class of all hyperplanes. Okay? So script H just simply is the set of all functions that can be represented as w dot x plus b. It's 1 if w dot x plus b is greater than 0 and it's minus 1 otherwise. So it's basically the family of all hyperplanes. So every hyperplane is parameterized by w, its weight vector, and b, its offset. And of course, it's not a unique parameterization because wb and awab, which is multiplying everything throughout by a scalar, give you exactly the same hyperplane. Okay, so this is w dot x plus b is equal to 0, and aw dot x plus, you can multiply this throughout by a and you get back the same hyperplane. So we need to normalize the representation somehow, and so we are going to have a canonical representation for the hyperplanes in this way. Every hyperplane would be represented by minimizing this quantity, w dot x plus b, over all the data points, x1 through xr, if there are r data points. Okay? So every hyperplane now has a unique representation, and that's the family script H. Now, in this family script H, I'm going to construct a hierarchy. So there are going to be sub-hyperplanes. So not all hyperplanes are equally good. And how do we construct this sub-hierarchy? Okay? We define script HA, okay, to be the set of all hyperplanes whose weight vector is bounded by A in this canonical representation. Okay? What that geometrically means is that you draw balls around each of your data points, and the radius of the ball is 1 over A. And you consider all hyperplanes that don't collide with these balls. Okay, so that's a subset of the set of all possible hyperplanes. And as A goes to infinity, okay, script HA basically becomes the set of all hyperplanes. As A goes to infinity, these balls shrink, and so basically the class of hyperplanes grows. So you've created basically a family like this. HA1 contained in HA2 contained in HA3, where A1, A2, A3 are an increasing sequence. And it created a nested hierarchy of hyperplanes. Now you can use actually an old result from the 60s, which says that the VC dimension of this class is actually bounded by A squared. So now you've got hyperplanes whose VC dimension can be controlled in this manner. So what we have is, remember that we wanted to minimize the expected risk over a family of hyperplanes. We don't have the expected risk, so we decided to approximate the expected risk by the empirical risk plus a complexity term, which depends upon the VC dimension of the family of hyperplanes. You can turn this around to minimizing phi subject to the empirical risk is equal to 0. Okay? These two are actually equivalent to each other. Which in this case, because the VC dimension of hyperplanes is actually just simply the norm of W, it reduces to minimizing the norm of W subject to this constraint. Now this constraint actually is just telling you that all your data is correctly classified. Right? Because yi takes on values +1, -1. Wx plus b can be greater than 0 or less than 0. If y is 1 and Wx plus b is greater than 0, or if y is -1 and Wx plus b is less than 0, it's correctly classified, and so their product would be positive in both cases. In all other cases, the product would be negative. So putting in this constraint for every single data point is basically saying all your data points must be correctly classified. This one comes because of the normalization that you've used, and essentially that's an equivalent formation. Now actually you can introduce Lagrange multipliers for each of the constraints, form the Lagrangian, do the standard thing, and it turns out that the hyperplane W opt has a representation in terms of the data points. These alpha i's are the Lagrange multipliers for each of the data points, and the optimal hyperplane is actually the sum alpha I, yi, xi, where these are actually the expansion over all the data points. So this means that the optimal hyperplane, there's another interesting fact that you have the Kuntaka theorem, which says that the product of the Lagrange multiplier and the constraint must be 0 for such optimization problems. And this means that if this is non-zero, then alpha has to be 0. Okay? So alpha will be 0 for many data points for which this is non-zero. So for many of the data points, alpha will be 0. For some of them, alpha will remain. And so only some of your data points will appear in this expansion. Now we're going to look. So this will be a sparse representation of your data in some sense. So you've got all your data points, your stops and your non-stops. And it turns out that the optimal hyperplane will have this expansion, and most of these alphas will drop out to 0. So you have you picked out a subset of stops and non-stops in terms of which you will represent your optimal data hyperplane. Now, we can look at when these alphas turn out to be 0. Okay? These alphas turn out to be 0 if yx plus b is actually not equal to 1. And alpha is non-zero if this is equal to 1. If this is equal to 1, that means the data points lie on. So here's the true separating hyperplane, w dot x plus b equal to 0. Here are two parallel hyperplanes, w dot x plus b equal to 1 and w dot x plus b equal to -1. Now all the data points on which alpha is non-zero actually lie on these parallel hyperplanes. Okay, and the rest of the data points which are far away actually lie further away. Okay? So basically what you have done is that you had a bunch of data points of stops and non-stops which were in a high dimensional space, and you found a hyperplane so that going at right angles to that hyperplane along that one-dimensional line, you can actually project all your data, and stops and non-stops can be represented by that one-dimensional projection. That's one thing. Yes. The second thing is that you've also found boundaries. So these are actually stops which are most like non-stops, and these are non-stops which are most like stops. And you can actually look at the non-stops which are most like stops and do a phonetic analysis of them to see which ones actually fall in this class. So given a whole bunch of data, you can actually use this as a way of sort of generating certain confusable pairs out of it. Now, the last thing which I should say is that after all, hyperplanes are not necessarily the best classifier. So we need to have some mechanism for nonlinear classifiers. And the way that's done is actually by transforming from the original space X to some new space Z nonlinearly, and then using your linear techniques in the new space Z. So that basically you have ultimately at the end of the day a nonlinear classifier. Okay? So ultimately at the end of the day, your nonlinear classifier would look something like this. Okay? I should say that this transformation is controlled by means of a kernel function, like the radial basis functions, which are also used in a different neural networks context. You basically perform this mapping from X to Z using a function psi, such that if x1 and x2 are 2 points in X, and their images are z1 and z2, the inner product of z1 and z2 is given by a kernel on x1 and x2. Okay? You can actually show that Z ends up being an infinite dimensional Hilbert space. This satisfies the inner product in that space. And essentially what you've done is you've taken your data from your original space, mapped it into an infinite dimensional space, and used linear techniques in that infinite dimensional space. Okay, that's how you get nonlinearity out of it. Now, I should say, having said all of this, that this is one of many competing schemes that you could use to essentially find the best nonlinear operator that will separate stops from non-stops. Because that is really what we're after. We have stops and we have non-stops. We have a particular kind of representation, and we want to find the best nonlinear operator to do that. And we have to think about some issues. We have to think about how large should the family of functions be from which we are going to search for the nonlinear operator, how much data do we have, and we need to control these two, the data points and the complexity of the family of nonlinear functions against each other. So in some sense, this would be like non-parametric regression. And you could use as a complexity term the VC dimension, the minimum description length representation for your family of functions, or the smoothness of your family of functions, and then you would end up with splines, as in the standard way. And all of these, I suspect, would give roughly similar results. Of course, I've not tried all of them, but at the end of the day, you want to know, this is the one-dimensional line parallel to that hyperplane on which you can project all the stops and non-stops. And so this is how the non-stops are distributed, and these are how all the stops are distributed. So we have some very high-dimensional representation of stops and non-stops, and we projected them to one line where we can draw nice histograms and show separability. Okay? Now, how does all of this work? Because all of these functions are really operators, because they're taking one time series and generating another time series if you're operating on it with this function. Right? So here's a sentence of Tibbet. She had your dark suit and greasy wash water all year. These are all the stops in that sentence. The and dark, D and K and so on. So this is what we would like. Okay? And this is what we get by using an operator like this. So you can see it's basically pulling out these stops. So this is just an example to give you a feel for how, when all is said and done, the output looks. Now, of course, this is not enough. This is anecdotal. So we need to plot actually false acceptances versus false rejections for such a detector. Because remember, the detector could say everything is a stop, and then it would have got all the stops and everything else too. Right? So you need to actually measure. It's also called type 1 and type 2 errors in statistics. But so as you vary the threshold of acceptance, you will plot out an ROC curve. This is the ROC curve that you would have got if you had used the basic original idea of computing derivatives, which is the burst landmark of Ken Stevens. Okay? This is actually if you compute an optimal linear operator, because a derivative is actually a differential operator is just one linear operator. Okay, and so you can compute the optimal linear operator. And this is what would be similar to the support vector machines in a time series context, would be what you would get if you use the nonlinear operator. So basically, the intuition has remained the same. If you're looking for particular transitions in the representational space, and we want the detector to fire whenever those transitions occur, but by using more and more complex families of functions, we can actually get equal error rates. We can get ROC curves which are increasingly better. Now this star here, this star is actually how an HMM does on getting stops. Now what do I mean by that? It's actually a very good HMM. It's standard in some sense, but it's trained on large amounts of data. It's a Bell Labs standard in some sense. And what we did is that we ran it on speech and did a forced segmentation of the speech signal with the HMM, and counted how many times it got a stop when there should have been one, and how many times it postulated a stop when there was none. And so you would get one number for false acceptance and false rejection. Because the HMM is not running in detector mode, where it's actually trying to detect stops. It's basically transcribing the signal for you. Okay, so this is the star, which tells you how well an HMM does. So as you can see that why has this improvement come about? It's come about mostly because we are actually using a representation in which stops best express themselves. Okay, and then on that representation, of course, we are constructing intelligent classifiers. And one could do that, of course, for all families of functions, but let me tell you more about stops, okay? Because this opened a can of worms for us. So this is one particular directory of speakers in the TIMIT database. There are 32 speakers in this test database on which you take 1 point. You take 1 point in this ROC curve, okay, and you compute the false acceptance and false rejection. This is the average across all speakers. So this is across all speakers in TIMIT, by the way. Okay, so this is speaker independent. So this is the average across all speakers. You can ask, how does it decompose by speakers? Are there some speakers on which it does well, some speakers on which it does badly, and so on? So this is actually 32 speakers in a particular database, and you can see you would ideally want them to be all here, low false acceptance and low false rejection, and most of them are, but there are a few outliers on whom it does really badly. Okay, like this one in particular is way off. So let's look at what the detector is doing for this. This is what the detector output looks like for the speaker. So I showed you a case of a detector output which looks pretty good. Right, on one speaker where you had clean speech. I mean, it wasn't any cleaner, but it was speech where the stops were all picked out. This is an example where the detector has failed. In some sense, we always learn more from our failures. So this, you can see what's happening. It's basically firing a lot. So you get a lot of false acceptance. And actually, it turns out that this speaker had two problems. One is that the speaker had vocal fry. So he was glottalizing throughout, speaking with a very creaky voice, and you actually got firings at the pitch pulses. Okay, and he also had a very low pitch. So at every pitch pulse, this stop detector was firing. The other thing is, the speaker had some unusual labeling, it's not entirely unusual, but it shows some variation in stops. For example, there's a lot of prefrication in the K. So the detector fires when the burst happens, okay, here. But the stop has, in some sense, according to the labeling of TIMIT, the stop has really started, the burst has really started from here because it's a prefricated burst. Okay? And so the detector which fires here catches the burst, but it's very far away from the true closure burst transition as labeled by TIMIT, and so it's deemed a false acceptance. Okay? In some other cases, like here, the stop consonants are very weak. So this is labeled as a P closure P in Timid, but you can see that the burst is almost non-existent. Okay? I should say that Timid labelings are about 20% off on the accuracy of this transition of closure to burst. So when you're trying to evaluate your detector, the detector is postulating points in time when a closure burst transition occurs, and there's a true Timid labeling, and if that Timid labeling is 20% off here and there, it's a difficult task of how you measure accuracy. So all of what I'm telling you actually has a 20 millisecond margin thrown into the acceptance of the stop detector. So this is about stops, but now you can actually measure this same thresholds on telephone speech. So remember, we started out by saying that somehow speech recognition falls apart when the channel changes and the acoustic environment changes, and somehow what we want is an entry point to understanding what's going on when this happens. Okay? If you have a 2 million parameter system, there is no way in which you can meaningfully take your system apart and get some insight into what's going on when the channel has changed. Okay? So this, I'm proposing features as an entry point to understanding. And so this is that entry point. We take the stop detector and see what happens when you have telephone speech. So you have timid and you have n-timid. Okay? So this is actually, so detectors have all been trained on timid. I should also say that the detectors have been trained on only 4 speakers of timid. So it's trained on very little data, and it does pretty well. Okay, this is because, of course, again, we've chosen representations in which stops are very well expressed. Now, so all these detectors are trained on 4 timid speakers, and this TT is the original threshold, original ROC curve for trained on timid and tested on timid. This NT is trained on timid and tested on n-timid, and you can see there's a huge change. Okay, some of the detectors don't work on n-timid. And this is actually trained on n-timid and tested on n-timid. Okay? So what's going on? Why is this huge drop in accuracy when the detector which has been trained on timid is suddenly turned to n-timid? So,
did you try the other conditions? Did you try training on n-timid and testing on timid? Is that
yeah, it's asymmetric actually, yeah. Training on n-timid and testing on timid is, okay, so I plotted 3 of the 4, right? So this is actually trained on timid, tested on timid. This is trained on timid, tested on n-timid, and this is trained and tested on n-timid. Now, trained on n-timid and tested on timid lies somewhere over here. Now, I don't remember whether it's better or worse than NN. I need to get back to you on that. But let's look at the outputs. So here is the speech signal. This is the timid output. And the same speech signal is, of course, has an n-timid version. So for those of you who actually don't know what n-timid is, timid is this database with regular speech, and n-timid is you take this database and put it out over the telephone line and recollect it at the other end. And so you have a telephone version of timid. Both of them are aligned. So you have 2 sentences aligned against each other. One is a telephone version and one is a regular full channel version. Okay? So it's the same sentence, and this is n-timid. This is the output of the detector on this n-timid version. And maybe it's not clear to you, but the general patterns of firing are the same. But the dynamic range has gone down a lot. So where there you were between 2 and 0, here you are between 1 and 0. And so the dynamic range of your detectors have gone down a lot from timid to n-timid. Now, why might that be happening? Okay. Why might the dynamic range go down? So we started looking at timid and n-timid and what's going on in the transformation from timid to n-timid. Now, sometimes the explanation is very simple. Here is a T closure and a T in timid. This is the n-timid version, which has also been labeled with a T closure and a T, but the burst, as you can see, has gone. Okay? So sometimes a telephone can do drastic things, okay? And here there was a burst which was to be detected. Here you can see a very faint trace. If you look closely, there is a very faint trace of a burst, but it's almost not there. So I don't know what the detector should really do on the n-timid version. Should it be actually trying to detect a burst when really it seems like there is none? Or should it actually be trying to detect a burst? Now, the labeling says that there is a burst here. But that's simply because no one relabeled nTimid. They just took the timid labeling and then applied it to nTimid. Okay? So some of the explanation is partly in that. But actually, there are two differences between timid and nTimid, roughly speaking. Okay, the two differences are there is a change in signal to noise ratio. Okay, and timid has about 43 dB SNR, and nTimid is much lower, like 30 dB SNR. And the second is this, so it's much noisier. The second is that a lot of the high frequency energy goes off in nTimid. Okay, so those are the two main things. Here is a plot of the drop in detector output between timid and nTimid for every single stop versus the drop in global SNR between timid and nTimid. Okay? So you have timid and you have nTimid. Every sentence, you have whatever, 1,000 sentences, let's say. Okay? So they are paired, timid and nTimid. You compute the global SNR for every sentence in timid and the global SNR for every sentence in nTimid. If there are 5 stops in a particular sentence, all those 5 stops will have the same value for global SNR in timid and the same value for global SNR in nTimid. Okay? So the global SNR only depends upon the sentence and not upon individual stops. But here you have global SNR, drop in global SNR from timid to nTimid, and here's drop in detector output. And you can see there's a faint correlation, but not really much. So just a global SNR is not really telling you whether stops have. So we got more fancy, and we plotted the local SNR. Okay. So what do I mean by the local SNR? The local SNR now is for every single stop which exists in timid and has a corresponding nTimid equivalent. You can compute the total energy in the burst and the total energy in the closure, and basically that'll give you a rough estimate of the local SNR. And you can do it for every single stop following the timid labeling. Okay, now the timid labeling may be off, but it won't be off by that much. So you'll get basically some statistical correlation. And you can see the local so this is the drop in local SNR between timid and nTimid, and this is the drop in the detector output, and now you have much more of a trend showing up. Okay? So it's the local SNR between timid and nTimid, and then we did something even more fancy. Now the timid labeling can be off, right? The timid labelings and stops are small things. So the bursts are of the order of 10 milliseconds. If it's off by 10 milliseconds in the labeling of bursts, you can see you'll get quite a lot of noise in a measurement of local SNR. So what we did is actually we went there and we applied the detector and refined to find out exactly where the closure burst transition occurs. So we used the timid labeling and then sort of use that timid labeling as an initialization for the stop detector to find out exactly where the closure burst transition occurs. And then 5 milliseconds to the right of that, we measure the burst energy, and 5 milliseconds to the left of that, we measure the closure energy. So that's an indication of instantaneous SNR, if you will, at the closure burst transition for every single stop in timid and every single stop in nTimid. And this is what you get. So maybe all there is to timid and nTimid is just that the burst is eaten away by background noise. Okay? Now, John Talon, who thinks a lot about these sorts of things, suggested to me that we have computed SNR in time. So rather than taking global SNR as a useful measure, we started developing the notion of local SNR and instantaneous SNR, where SNR is a varying function of time, and it should be because stops are much lower energy events than vowels. And so you really should look at how well preserved closure burst transitions are in trying to detect stop consonants. But maybe you might want to separate SNR as a function both of time and of frequency. So it could be that the local SNR and frequency bands at different points in times are very good predictors of the reliability of your detector. Okay? So you have a detector, and you know that it fails from timid to nTimid, and you want to understand why it fails from timid to nTimid, and the explanation I'm postulating is that it's a local SNR which tells you how well the stop detector will work. It's a predictor of how well stop detection will work. Now, I don't know how well humans detect stops. I also don't know how well humans detect stops in the presence of noise. Okay, a lot of speech perception has been done on categorical perception type things. They've not been done in the detection mode where you're actually giving continuous speech and there are obvious cognitive overload effects that you have to take into account. We're actually trying to detect stops. And so there's been a rich tradition in speech perception and acoustic phonetics where you talk about cues that the burst has in determining place of articulation for stop consonants, or cues that the burst provides in voice onset time. Okay, so these notions of the measurements near the burst have been invoked in explanations of speech perception and cues for speech perception. And any satisfactory account of speech perception has to explain how this burst is actually detected by some perceptual apparatus. And this is one postulated mechanism for detecting it. And then the question I have is, what happens in noise when there is no, when the burst becomes much poorer? Do people maintain the same place of articulation but now start confusing manner? So that stops and fricatives start sounding the same because they are basically one noisy mess, but the transitions into the vowels remain because they are, there's more SNR in those regions, and therefore the confusions are across space and manner. Now, I've already taken a lot of time on stops, and there's a lot more that I would like to say about it, but let me just briefly tell you that stops are not the end of the story if you want to build a system. You want to actually have broad classes. So this is, you can imagine doing basically the same thing for every single phonological class. Come up with a representation in which you think the acoustic properties of that phonological class best express themselves, and in that representational space essentially construct a recognizer or a classifier. Okay? So for nasal, for sonordants versus obstruents, which is also one of the first sort of distinctions that are made in the phonology and the acoustic phonetics literature, it turns out that these four things were good measurements to make. And we had two classes of detectors. Those based on periodicity, using the notion that sonorant sounds are more periodic than obstruent sounds, and those based on spectral balance, because obstruent sounds tend to have a lot of high frequency energy, whereas all the sonorant sounds tend to have well-developed form and structure, and they have a lot of energy in the form and reasons. Okay, so these two detectors actually perform reasonably well. And again, you can get the same ROC curves and go from here to here, and this is where the HMM does, and you can document performance and all of that. And I should also say that all along I've been talking about making one very good detector, and another whole direction of research is actually have multiple detectors and combine them to make one very good detector. Okay, and there are some interesting things one can say about how one can provably combine multiple detectors, provided they are uncorrelated, to get better detectors. I'll take another 5 minutes or so. I just want to make a few gestures to adjacent fields, okay? So some of the things that we were doing at Bell Labs actually were trying to recover acoustic correlates recover distinctive features from the acoustic correlates in the signal. And distinctive features also have obvious visual correlates. And so this is joint work with Eric Petterjan, who has a lip reading system. This is actually a sentence. It has two stops here, k and p. This is actually the word Cupid, just a snapshot of it. This is the stop detector firing for k and for p. And of course, k and p are very confusable acoustically, but visually they're very distinct. And this is actually the interlip distance for that speaker on k and p. So this is the interlip distance, and for p, the interlip distance goes to 0. So basically, the visual cues and the acoustic cues have a common articulatory origin. And you try to recover that articulatory gesture from the acoustic and the visual cues. And the second thing I should say, and this is from the work of Suga at Washington University, there are detectors in various in the cortex of various animals. So this is actually the bat. And here's a particular, so it turns out that bats also have a finite inventory of sounds, and they communicate with each other using this finite inventory of sounds, much like humans do. And here is a particular acoustic signal which has two components, you can see. Okay, there's a big sort of blotchy thing, and then there's a little one. This corresponds to this part and this part in the spectrogram. So let's call those two components A and B. Okay. So what they found is that there are certain neurons which fire rapidly when A and B are presented one after the other in this natural stimulus. When A is presented alone, there is no preferential firing. When B is presented alone, there is no preferential firing. When B is followed by A and presented, there is no preferential firing. So there literally is a grandmother cell out there looking at a particular constellation of acoustic properties and firing every time that particular constellation occurs. Okay? So one might ask, therefore, reasonably, what are computational mechanisms by means of which particular irregularly shaped objects in the time-frequency plane can be reliably detected? Okay, and that is, in some sense, the general question which this is one part of. So what would a feature-based speech recognizer look like? You would take speech. You would have a signal processing module with different representations, R1 through R3, just shown. Each such representation is one in which a particular phonological feature best expresses itself. In that representational space, you will construct an optimal detector that separates the positive instances of the feature from the negative instances of the feature. The outputs of those detectors can be interpreted as a posteriori probabilities. And so what you'll have at the end of the day is outputs which are showing the likelihood of a feature at every point in time. And those outputs will be used to access the lexicon, which is also represented in terms of features. Okay? Now, so you could do a finite state decoding. This part is sort of under construction. So you can imagine that you have outputs of these detectors like this. So the stop detector is firing with different strengths. Okay, so you have firing rates at different strengths. And the strength is basically telling you how likely that point is of being a stop-closure transition. And this is actually another transition detector we've made, which is a nasal to vowel transition detector. It turns out that detecting nasals by itself is really hard, okay? But detecting nasal to vowel transitions is much easier because there's a loss of second formant energy as you move from the nasal to the vowel, okay? So you have detectors like this, and what you want is, given an input in one language, that language is that sigma 1 is an alphabet which is made up of features. Okay, given an input in a featural representation, you want an output in a phonetic representation. Okay, so P. I once was talking to Maurice Halley, and he told me that there's no such thing as a P. It's merely a nickname for a constellation of features. It's a labial, plosive, and so really there are features and there is everything else, and phonemes are just nicknames. So anyway, that's an interesting point of view. So you take sigma 1 to be features and sigma 2 to be phonemes, and these are really, and you want to find a mapping from strings of features to strings of phonemes. And that's your decoding problem in some sense. Or this could be any other alphabet. It could be words really, ideally. But if you want to have phonemes as a symbolic unit in your language, then that's a reasonable choice. Okay? So I'm going to sort of conclude here. So in speech recognition, we have the interaction of a linguistic symbol system with an acoustic physical system. Okay? And there are good reasons. A lot of people have devoted quite a bit of thought to what would be appropriate symbolic units in terms of which we should represent our linguistic symbol system. And acoustic phonetics is supposed to mediate the mapping between the signal system and the symbol system. And the fundamental problem of speech perception is really perceptual invariance in the face of high acoustic variability. So the acoustics changes, the channel changes, there are competing speakers, you're going from a room with a lot of reverberation to a narrow claustrophobic room. There's perceptual invariance across all these widely varying acoustic conditions. That's a problem which we have not solved. Okay? And so in order to make progress on that question, which is a fundamental question of speech perception, and its technological counterpart is, of course, making a working speech recognition system in the real world. So if you want to make a speech recognition system for a handheld device where the acoustic environment is hard to control, you really have to think about it. you would want to think about various acoustic conditions which leave the signal, which leave the human subject perceptually invariant. I try to give you a sense of the role of speech production, the role of speech perception, the role of linguistics in the formulation of what are interesting problems in this whole approach. I try to give you a role of signal processing and the role of statistical learning, and both are extremely important. So it cannot be done without some statistical learning to capture variability along dimensions, to construct optimal detectors, for example. And of course, if you want to ground all of this in a neural context, there are detectors in animals, and though they do not perform the same functions as detectors in human language, and though they don't have the same capabilities as human language, certainly there are detectors for irregularly shaped objects in the time frequency plane. Okay? And it is not at all obvious how one makes detectors for irregularly shaped objects in the time frequency plane. So, yeah.
I was wondering whether you've given any thought to the problem that features have somewhat different acoustic realizations in different environments.
Yeah.
So you imagining modifying the representational space in a way that depends on the specific environment of occurrence.
Yeah, so they have different acoustic realizations in different phonetic environments, you mean? Yeah. So that's certainly obviously the next thing to do. So having criticized sort of the standard approach for using one-size-fits-all representations, I went and did precisely that in some sense. My stops all had one representation. I did not discriminate between stops of different flavors or of different places of articulation or also of different phonetic contexts. If you actually analyze the performance of my stop detectors, it turns out there's a huge difference between the detector performance in syllable initial stops, which are very well articulated and have a clear closure burst transitions, and syllable final stops, which are much less developed. So obviously there's a lot more work to be done. And that's something that one needs to think about. This is really, in some sense, trying to force people to begin to deal with real acoustic questions in the speech signal. And the speech recognition community, for the most part, really takes the speech signal, develops a representation of it, like Kepstra or so on, and after that they forget about the fact, for the most part, that it is speech. It could just be an exercise in modeling time series. Here, in contact with how the acoustics varies as a function of phonetic context, as a function of speaker, as a function. And it turns out actually there's not that much speaker variability in stops that we've noticed, which is sort of interesting. But there's a lot of variability by phonetic context. Syllable position for sure, and even other things, clusters.
I wonder if you just look at the, you've done the following experiments. So your voicing detector, look at what the probability that assigns to, say, P or B as you vary VOT, and what the shape of that curve is, and how does that curve look as compared to the kind of curves you get with human categorical perception. Do you get sort of categorical effects, or do you get kind of a sort of slowly decreasing?
So from the automatic detection scheme.
So from the sort of optimal detector that you got,
Yeah.
Given the sort of class of models that
Do you get categorical
do you get
perception?
categorical perception?
Actually, you do. So I showed you I showed you stops versus non-stops plotted along that one-dimensional line parallel to the hyperplane.
Right.
And there you do get those very clearly separated. Voice onset time, also you can actually plot these distributions, and you get two very widely separated distributions. Now, so there are two things.
Those plots were what?
So there are two kinds of plots. There's one kind of plot that you can make by manually constructing the voice onset time for every single stop.
Right.
And plotting the separation. There's another plot that you would get by running your automatic detector and getting an estimate of the voice onset time and plotting the separation in the voice on the estimated VOT. The estimated VOT is an approximation to the true VOT, and it's off about 20% of the time. And you get categorical perception in both. And in fact, does that answer your question? Or?
I noticed that you don't introduce a language model in these things, and I was wondering if maybe you're sort of cherry picking the features that are most likely to be separable. Let me give you an example. Nasal sounds are hard enough to understand in English. If they were in Czech, I'd have an even harder time to understand it. So maybe there isn't enough information in the signal itself to separate out nasal sounds at all. So that what we do is really more of a cognitive thing.
Yeah, so that's so let me respond to that at a number of different levels. Okay. First of all, there's a reason why I've left the language model out of all of this, because it's my belief that we are able to decode nonsense words. Okay. So when I produce a nonsense word to you, you would be able to decode it reasonably well. Otherwise, you would never be able to learn a new word, because the first time you learn a new word, it is effectively a nonsense word for you. Okay. So given that we are able to reasonably decode nonsense words, and given that that is actually where current speech recognition technology is worst, it's reasonable to compare modern speech recognition without the language model on nonsense word recognition. Okay, so that's really the motivation, to try and get at acoustic phonetics. Now, having said that, human recognition rates on nonsense words are actually, so the error rates are actually higher on nonsense words than they are for words which have sense. So Miller actually did this in the 60s also. Shortly after he did all of this, is that he plotted error rates as a function of a number of variables, and semantics was one of them. Okay, so you are bringing higher level knowledge in the decoding process, and it remains to be seen to what degree you bring that higher level knowledge. So maybe in noisy conditions you do, or maybe you don't. It's an important question, and it has to be resolved to understand better whether the current failings of the speech recognition system are reasonable or unreasonable. At the outset, you would think it's unreasonable for the recognition system to fail when on telephone speech. Okay? But on closer examination, you might find that precisely those sorts of things happen. That actually stops are not well preserved in telephone speech, or that F and S, for example, clearly is very hard to tell on a telephone even for humans, because all the energy is at a high frequency level, which is cut off. Okay? So there may be certain phonetic differences which are very hard to tell apart in the absence of higher level knowledge. But this is really an exploration of that issue to some degree.
I want to point out something about, of course, HMM. I mean, obviously, our current formulation has the gigantic advantage that it's completely uniform, that everything is an HMM, that everything is estimated by, the forward-backward algorithm or EM or whatever, and that there is just one formulation, and you just let your machinery go, and it goes. And the fact that it hasn't changed, actually, not 15 years, it hasn't changed 25 years. The wheel didn't change for millennia. And it's not the wrong solution to moving things from here to there. Although some of us can't move it with wheels, we need motors also. But the wheel is still involved in it. So I don't think that the criticism that it hasn't changed, carries much more.
So just the fact that it hasn't changed in and of itself doesn't mean anything at all.
Right.
The point is it hasn't solved the problem. Okay?
Yeah,
so given that it hasn't solved the problem, now you can be an apologist, or you can try and do something different. All right? So now,
Or you can refine it, etc. I mean,
you can refine it, but what has been the refinement in the last 25 years? An n-gram backend, an HMM model, and a textual front end. What has been the refinement?
well, but I mean, obviously, what you're talking about, you know, you have decades to get it done, all right? Because the way you're going to combine things, and you have to worry about what Luigi said over there, whether some detectors need to be adjusted for different environments and all that. And what you're lacking is exactly what HMM has. Namely, what you're lacking is the uniform way of approaching. And you'll have to try this and you'll have to try that.
No. I don't think that's a fair characterization. I think it is fair for you to say that I have made minimal progress. That I think is fair. I have only, after all, made a stop detector which works reasonably well in syllable initial stops. Okay? But it's unfair to say that progress along this path is ad hoc, that I'll try this, I'll try that, there is no principle. I've tried actually very hard to communicate to you the principles behind such an approach. That there are some principal problems that you can set up and provide principled answers to. And yes, they are not the complete solution, but it gives us, as I said, you know, it's hard to define what insight is, but I'm hoping that you have some insight into why stops are a problem in going from clean speech to telephone speech. Okay? Now,
but let me just say a little bit more. Like, first of all, of course, the way you want to do it is the way they did it before we started working at IBM. So before 30 years ago, that's the way they wanted to do it, the way you just described, right? Secondly, you know, they would come to us, and you know, we had all these people put into our group who were allegedly experts, and they were phoneticians and syntacticians and this and that and the other thing. And one of the guys would say, well, I'll just write a little grammar, you know. And, you know, n-grams were better than the little grammar you would write. So I am skeptical about it, not because, you know, HMM has, you know, has solved the problem, because it obviously didn't. But because the approach that you are suggesting is the approach that everybody jumped at to start with.
okay, so let me respond to that. So this is actually the oldest argument that I've heard in the book, okay? So I have a...
you can't expect, you know...
No, so let me say this. Okay, the first time I proposed, let's look at feature-based approaches. This is exactly what I was told. That it's been tried and it doesn't work. Okay? So I went and actually started looking at what exactly was tried and why it didn't work. Okay? Now, first of all, it was completely non-statistical.
That is true.
Okay? Everything that I presented to you is acknowledging the fact that we have to use statistical methods and there's no way about it. Okay? So constructing a feature-based recognition system in an expert system type context where you're I agree, that work was actually just plain bad work. Okay? Maybe I take that statement. Okay. Maybe it's not just plain bad work. You have to judge these things in their proper context and the times. But it was work done in a context where you build expert systems with rules thrown in, and it had problems. You had to tinker with it. It was brittle. There was no natural way to capture variability. And all of those were actually solved by HMM. So the transition from pre-HMM to post-HMM was actually a very important transition. Okay, and it has taught us something. It did capture certain first-order effects of speech, that it has temporal variability, that we need to capture variability basically spectrally and temporally, and it did that. Okay, but that was, you know, some time ago, as we discussed, right? So now I'm saying let's revisit some of the issues they were looking at in the 60s and 70s, and maybe they had a few good points, and I think they did. But let's revisit them in a more modern context where we can use the general knowledge that we have gained from our years with HMM-based speech recognition to redefine questions in that framework. Okay? So I'm using that feature-based point of view to really define what are useful questions. But I'm using essentially all that I know about statistical learning theory to provide workable answers.
Can I ask a non-philosophy question? I wanted to ask about the final slide on the stops that you showed correlating the reduction in the output level and the instantaneous signal-to-noise ratio.
Right.
What I'm a little worried about is what you're actually, you've got a linear classifier. And I'm really worried, I'm curious, is it possible that what you're really measuring is in a sense correlated with the amplitude of the excitation to the final stage of your linear classifier? In other words, what you're really measuring is correlation with the input to a linear classifier.
Actually, the classifier is nonlinear in that, I remember I had 3 stages of classifiers.
Yeah, I'm wondering by the time you've gone through essentially your y-axis, you understand you've measured this extent. And I wonder if by the time you've gotten to that point, what you've really done on your stages of your classifier. I'm just trying to start at the head, so I'm hoping you address it because it's bothering me.
So let me understand your question. You're saying that suppose I had a linear classifier, then whether I was measuring the correlation of my classifier outputs with,
Well, your y-axis is measuring signal-to-noise ratio.
yeah, is a drop in signal to noise ratio. Actually. Yeah, yeah, between timid and intimate. So for timid, I measure the local signal to noise ratio for a particular stop, and I measure the local signal to noise ratio in intimate for that same stop, and the drop between those two is on the y-axis. Let me just put this up. Actually, I take it back. Maybe they were linear. They were. Yeah, they might have. Yeah. So this is actually the drop in SNR between timid and intimate, and this is the drop in detector output between timid and intimate. Now you're saying this correlation might be spurious.
Not spurious. I'm seeing you're measuring the correlation in the output of the drop in output of the linear detector with the input. And it's really surprising that you drop.
So the idea is that the instantaneous SNR looks very much like actually as one of your inputs, the way you measure it, right? You're measuring the energy.
Yeah.
It's like a derivative essentially. That's like
What's your question exactly?
Good question. If that's the case, well, I'm not sure. I mean, if that's the case,
This didn't tell us anything.
yeah. No, I mean, I wouldn't put it that harshly, but I would. I mean, I guess the thing is, given the way the y-axis is confused, I'm not sure it's actually getting into true signal-to-noise ratio in the channel, and it's.
Right, so I suppose another way to put it is to say that your detector doesn't necessarily look at the signal-to-noise ratio. It looks at a sort of peculiar form of signal-to-noise ratio on the left and right side of the actual stop release.
Right.
And this is basically plotting that versus detector performance. And so in that sense, it's not very surprising. In that sense, it's not very informative.
You're saying that, yeah.
And furthermore, this was actually, the location was obtained by your detector, so it's even further correlated to your detector's performance by the very virtue of.
Yeah. No, but that is really to get the true, that first detector is really just to get the true closure burst transition.
Okay, I know. I suppose I'm taking issue with that as well, saying that that's not the true closure burst transition, but
I see.
the transition as estimated by your detector. So that's where the detector thinks the transition is taking place. So that's
Yeah. And so,
In other words, I guess I would restate it and say that instead of really measuring signal-to-noise ratio across the channels is really measuring the strength of the excitation to your detector across
Right.
channels.
Strength of the excitations of your?
Yeah, say drop in excitation across channels to your detector.
No, it's a valid point. I'm trying to think of whether, so the drop in instantaneous SNR is roughly correlated with the input to the detector. That's what you're claiming, right?
Change in
Yeah.
input between Timid and Timid. In other words, Timid got a certain kind of excitation, and one characterization of the excitation is the energy to the right over the energy to the left of the burst. And so this is a change in excitation between Timid and Timid. One of the three features that make up the input to your classifier.
And this would be the same for a nonlinear classifier?
I'll bet it would be different for a non-linear classifier, and that would be a problem.
No, it is the same for, I mean, this trend is preserved for linear and nonlinear
Yeah, well, then
classifiers.
the non-linear one, I think, would be interesting.
Yeah, in case this was the nonlinear classifier, this would still be an interesting. Then it would still be an interesting
Would be interesting.
correlation.
No, it is the same between, it's roughly the same between linear and nonlinear. But I'm trying to understand why why it would be
In other words, the slope of this line could be the weight parameter that associates with that particular input, one of the three input features.
yeah, you need to work this out actually. Because you can basically take your, you're saying that you can take the derivative of your operator. So you've got y as h operating on x.
Yeah,
And-
let's thank you once again.
Yeah,
We can continue
yeah.
the discussion. Yeah, that way you can let the camera guy go.